In this module, we will discuss the chemical potential of individual pure substances. What if we have a system consisting of a single pure substance? In this case, the chemical potential of the substance is equal to its molar Gibbs energy. As such, it is a function of only externally controlled temperature and pressure. Based on the fundamental equation of thermodynamics, the differential of molar Gibbs energy is equal to the negative of the molar entropy times dT plus the molar volume times dP. According to the properties of total differentials, the partial derivative of molar Gibbs energy with respect to temperature at constant pressure is equal to the negative of the molar entropy of the substance. Similarly, the partial derivative of molar Gibbs energy with respect to pressure at constant temperature is equal to the molar volume of the substance. In general, the physical quantities entropy and volume are always positive. The implications of these relationships are illustrated in this figure. It presents the Gibbs energy of an arbitrary closed system as a surface in a three-dimensional plot, where temperature and pressure are independent variables. When the temperature increases at constant pressure, the Gibbs energy always decreases. Conversely, when the pressure increases at a constant temperature, the Gibbs energy always increases. These considerations also apply to the chemical potential of a pure substance. As is often the case in chemical thermodynamics, we first consider the standard chemical potential of a pure substance. It indicates the chemical potential of the substance in a standard state. The standard state implies the conditions of constant pressure equal to standard pressure, thus leaving only temperature as a variable. Just as the absolute value of the internal energy of a thermodynamic system cannot be determined, the absolute chemical potential is also indeterminate. However, we are primarily interested in the changes in chemical potential upon a change in the system's state. A simple way to calculate the change of the standard chemical potential of a pure substance upon a temperature change is to refer to the definition of Gibbs energy. Gibbs energy is equal to enthalpy minus temperature times entropy. Using this definition, the change in the standard chemical potential upon a temperature change from T1 to T2 is given by the alteration in this parameter combination, calculated per mole of substance. The difference in molar enthalpy at two temperatures can be taken to be equal to the difference in the standard enthalpy of formation. The resulting equation for the change of the standard chemical potential of a pure substance contains standard enthalpy of formation and the standard molar entropy of the substance in question at respective temperatures. These values can be calculated using the reference data. For pure substances in non-standard states, the chemical potential varies with both temperature and pressure. We can express the chemical potential as the sum of its standard value at a given temperature and another term accounting for pressure dependence. The pressure dependence of the chemical potential is derived from the total differential of the Gibbs energy. Specifically, the derivative of the chemical potential with respect to pressure at constant temperature is the molar volume. Thus, the pressure-dependent contribution to the chemical potential at a constant temperature is given by the integral of the molar volume from standard to the actual pressure. To obtain some specific formula from this general expression, we will consider two limiting cases. Solids or liquids can be considered incompressible. and we can assume that their molar volume is constant. In this case, the integral gives a very simple expression. The chemical potential as a function of temperature and pressure is equal to the standard chemical potential at this temperature plus molar volume times pressure difference. Note that specifically for condensed phases, the chemical potential is determined by the total exerted pressure. However, due to their small volumes, the pressure influence on the chemical potential of a condensed phases is minor and is typically neglected. For an ideal gas, its molar volume solely depends on its pressure. This dependency is given by the ideal gas law. By integrating the molar volume from the standard pressure to the actual pressure, we derive a formula connecting the chemical potential of the ideal gas with its temperature and pressure. The chemical potential of an ideal gas equals its standard chemical potential plus RT times the natural logarithm of the ratio of the gas pressure to the standard pressure. Interestingly, this formula consists of two distinct components. The first is the standard chemical potential, an inherent property of the gas determined by its chemical nature. The second, the term RT times the natural logarithm of the pressure ratio, is derived from the ideal gas law and is not specific to the particular substance. Due to their significant molar volumes, gases have chemical potentials that are strongly dependent on pressure. Notably, in a mixture of ideal gases, the chemical potential of each gas is determined only by its own partial pressure and is unaffected by the presence of other gases in the mixture.